Alright, welcome back. This is part 2 of the video. It's really module 18, serial communication. But again, like I said, I like it to be a little bit closer to the synchronous SPI, LCD stuff we did. Again, SPI is that synchronous version, but specifically stands for serial peripheral interface. I wrote that right there. That's SPI, so that is a synchronous version of serial communication. SPI being the protocol. Now we're moving to asynchronous, and the protocol is Universal Asynchronous Receiver Transmitter, or the UART. All right, so asynchronous, no clocks. How do they communicate? How do I know what this information is supposed to mean? For example, if I have an ASCII character, right, those are 2 bytes. I'm sorry, it's 1 byte of data. So if we take a look at our ASCII table, we do something along the lines of 0x48, so that's the hex representation. That represents a capital H. So 0x48 though is a bunch of bytes of information. So how do I know, sorry, not a bunch of bytes, a bunch of bits of information. How do I know when a packet or a frame, one frame starts and begins? So key thing, first thing, we have to have the same baud rate. Meaning each device, the MSP432 and then the other device that's connected to, or maybe a computer and the MSP432, they need to know that they're transmitting data at the same rate, or they need to both know how fast data is being transmitted. Per second. 9800 baud, pretty common baud rate. We use that a lot in ECE 210 when we're using it with the Arduino. Remember, we set up that serial interface with the baud rate 9800. All right, so each one has separate clocks, so they're not on the same clock like we saw with the serial peripheral interface. Separate clocks, but they do need to be within plus or minus 5% of each other. And that allows to make sure that I'm at least accepting the bits fast enough to know what's going on. All right, so we synchronize over a start and stop bit. And then a stop bit of 1. Or sometimes 1, 1, but specifically 1. All right, and we can see here, so information is going to be high, then it's going to go low. We know it's a start. Then we have a lot of the bits, so the actual data, and then we have the stop, and then stays high. And we know that this is a stop bit because we have agreed upon how many bits we're going to send each other per frame. And then also, as you can see, this is and the stop bit just allows us to know when to stop. So if it's high, then all of a sudden goes low, then we know we're taking information and we're good to go. All right, 2 flags. So we saw some flags last time, very similar flags here. And we're going to do a demo in class, but just wanted to get this out here for you. This website here has demos for the asynchronous and synchronous serial communication. We'll do those in class, but if you want to take a look. All right, so RX IFG is a 1 when the FIFO is full. And then for receiving, so now we know, hey, okay, there's data there, let's go grab it. For transmitting, it is a 1 when the FIFO is empty. I didn't write full on that last one. There we go. All right, so transmitter here. So we're transmitting. If this is a 0, then the FIFO is empty. We can push more data into it. It's going to all transmit bit by bit over the serial connection at the set baud rate. And then we are going to, as soon as data is there for us, we're going to set this to a 1. We know we can receive and pull information off that. Here are the same flag, or not the same flags, but flags that are for that same. So we still use a interface, same kind of interface, but we just set it to a different mode. So instead of SPI mode, we're going to go into UART mode. All right, let's look at an example. So we're not going to get as much detail. What I find is serial UART is very useful. I use it a lot in research. If you've ever seen the capstone, the robotics capstone, or the robotics, anything with the 495, working with the TI bot with a Raspberry Pi. The Raspberry Pi is sending data over UART to the MSP 432 to drive it. So we're sending a linear X value and an angular Z value. And the way I send it is basically just a X comma Z with a new line at the end. And that gets sent as an ASCII string. Basically, you can think of it that way. Or, the bits, the hexadecimal, all that is sent. The MSP 432 receives it and then pulls off this X and this Z to drive the robot accordingly. And so that allows us to have a smarter brain controlling the robot that can then talk to a whole bunch of different systems out there. So serial interface is really important. It's really useful. We'll see it throughout this class, but I just wanted to show you guys, get this up closer so that you can kind of learn it. All right, 0x33. We got our start bit here. So our frame is here to here. We get our start bit, then we have our data, and then our stop bit. Key thing to note, as this comes in, if we look at this here, in this example, I do it left to right because that's how we read, and it's easy to see that this is 3, 3, or the character 3. But what to note here is that data is coming in from right to left to right. So this bit gets sent first, then this bit, so on and so forth, and this bit is sent last. So this is not the order at which we got the bits. This is just an easy way to visualize it so that we can then convert it to hexadecimal and ASCII. All right, T, we got our start bit, our stop bit, and then our information, which is hex 7, 4, which corresponds to the character. These are characters, T. And one last try. You guys will get to practice this on the pre-lab. I don't know what just happened. I was just copying what was up above, I guess. And our stop bit. We got 0, 1, 0, 0, or 4, and then 1, 0, 0, 0, 8, which corresponds to H. Play around with this, practice it. We'll see it in the lab, and we'll get an example of that. All right, bandwidth. So think of bandwidth as the amount of data that is sent per second. So if I have a start and stop bit and 8 bits of data, my frame is 10 bits. My data is only 8 bits. So if I'm talking bandwidth, I'm only talking about the data. And so I have to use that as a ratio times my baud rate. So let's go with the general data frame rate, or frame, and times my baud rate. So if my baud rate is 9800 bits per second, and I'm sending 8 bits per 10 bits of data, then I'm looking at a ratio of 80% of 9800, and that would be my bandwidth, because I'm only using 80% of the bandwidth. 2 of those bits are being used for control. That's the gist of it. It's not very complex. It's very nice. It's very easy to use. It's very universal, obviously, and it has a lot of application. That's all I got for the synchronous or asynchronous portion. Here's a little bit, we've done this. By the time you're watching this video, you've done these already. Next time we're going to be looking at the Module 18 stuff in the lab. Later.